was a bit late to give you guys a bit more time to have a break, but clearly you're very keen for combinatorics since you're all here exactly at past. So we might go a few minutes over time just because we're starting a bit later. Okay, there's 2 challenge problems up there. There are several ways to do it, but the idea is for you to find a solution that uses pigeonhole principle. If you do not know what pigeonhole principle is, we're going to do it now. So then rather look at the examples we're going to do than try to do the challenge problems. How many of you did look at yesterday's example that we ended with? Anyone check that out? Still the one with the basically pyramid that goes up with 11 blocks at the bottom and pulls up to the top? Okay. I think let's continue on and just finish that one, and then we'll start with this lecture, which is about pigeonhole principle. Okay, so if you recall from yesterday, we basically drew a pyramid shape that kind of went on like this, and at the base, it had 11 blocks. All right. So it went all the way like that. And the question was, we needed to fill these blocks at the bottom with either zeros or ones, and for how many different arrangements of zeros or ones will we have if you add it up. So the sum of these 2 gives you the number in that block. For how many different arrangements at the bottom will you have a number at the top that is a multiple of 3. All right. So, considering that our lecture yesterday was about Pascal's triangle, that might be a bit of a hint. So if you look at this, consider we had a number here. Let's say it was a 1. In how many ways can that 1 be transferred or moved up to the top block? If it's in the block there, it can only go to there, only go to that square, and then go to this square. In the idea that if you have another 1 here, you would add them, would be 2, and if you had 1 there, you'd add them, and this would be 3. So this 1 contributed to that 3 by going this path. That roughly makes sense? But the 1 in the middle both contributed to the 2 on that side and to the 1 on this side. So it went up to be part of that 3 in 2 ways. It's one of the 2 ones there and the 1 here, and they both went up to make the 3. So this 1 was basically added twice in that sum. Well, this 1 was only added once in that sum. Let's put a 0 there. So we can basically say it went up 1 way, this one went up 2 ways, and that's how we got our sum there at the top. All right? So, let's work a bit from the top. How many ways can any value that's in the top square make it to the top square? It's just going to stay in the top square. So, it's literally going to be 0, choose 0. It's our top square going to be. Because it is there, it stays there, it doesn't go anywhere. Any value here can only go to the top square 1 way, by going up. And any value here can only go to the top square by moving 1 up. So both of them will have a value of 1 inside. Our top would also be 1. Now, like we said for this row, we said this one can only go up 1 way, but the value here can go up 2 ways. And the value here can again only go up 1 way. Starting to look familiar? So for next row, you can basically see it as, let's take this square, any value that's in here will either be added or will both be added to that square and to this square. And those squares will be added 2 times and 1 time. So this one will be 30, 1. And so we're going to work down, and you'll see it's Pascal's triangle. So if this is our technically 11th row down, but we call this one our 0th row, so this would actually be our 10th row, right? So for Pascal's triangle, that would be 10, choose 0, 10, choose 1. Okay. I'm sorry, I'm writing it in the values in the squares right now. That I should actually not do, because that might be a bit confusing. I'm basically saying that any value in here will move to the top in 10 choose 0 ways. Any value in there will move to the top in 10 choose 1 ways. Any value in the next one will be 10 choose 2. And so we'll go on. So it means if I put a 1 there, it will only move to the top in one way. So the maximum contribution that that 1 can have to the top value is being 1. But the next value, 10 choose 1, which is 10, means if I put a 1 in there, it will be added 10 times by the time it gets to the top. So it has an influence of 10 there. So if I had a 1 there and I would make it a 0, this value would decrease by 10. Okay. So that is the influence that each of these 10 values here have. At the end we have 10 choose 10. So we can basically make the value at the top, build it up, just based on the values we have at the bottom. So if we would write that out, let's call the value at the top S. We would have that S is equal to, now let's call this x1 that we put in there, x2 that we put in here, x3, and all the way, let's start at 0 to make it easy to compare to what we have in our choose function. And we'll go all the way to have x10 here. So each of these xi values, say xi, will be either 0 or they will be 1, because that's our problem statement, that we can only put 0s and 1s at the bottom. Okay, so our sum at the top will be 10 choose 0 times x0 plus 10 choose 1 x1, 10 choose 2 x2, and so on until we have 10 choose 10 x10. Great. So our question is, for how many arrangements will this sum be divisible by 3? Okay, so you are familiar with quads by now, right? But better than Monday. So we want to see when is this divisible by 3. It helps to notice that 10 factorial, because we remember what our choose function is, 10 factorial is 10 times, say 8 factorial, yeah. So there's a very clear multiple, two multiples of 3 in 10 factorial. So if we have 10 choose 0, that's just 1, so it's fine. We can just rewrite that as being x0. And 10 choose 1. The problem with 10 choose 1 is it's 10 factorial over 1 factorial, 9 factorial. Right, so that's only 10. This is not divisible by 3. So that doesn't help us yet. Let's look at 10 choose 2 though. So here we have 10 factorial over 8 factorial, 2 factorial. So there, we have there 10 times 9 over 2 factorial. And this is clearly divisible by 3. For our next one, x3, we have 10 factorial, 7 factorial. This is 10 times 9 times 8 over, sorry, that's a 3, meant to be a 3. And you have 3 factorial. Right, one of the 3's there will cancel, but there will still be a 3 left at the top, meaning this is also divisible by 3. Let's quickly check out maybe the next 1 or 2 terms. Okay, here we have 4 and 6. It's for, again, 10 times 9 times 8 times 7. And we have 4, 3, 2, 1. The bottom, again, one of the 3's will cancel, but there will still be a multiple of 3 at the top, still divisible by 3. And the last one is 5 factorial, 5 factorial. And you'll also see that this is only, there will still just be, 5 factorial at the bottom and 10, 9, 8, 7, 6 at the top. There will still be more 3's at the top than the bottom, meaning this is still divisible by 3. If we go on to x6, it will basically be a copy of this one because one of our factorial rules basically. And then same one there for 7 and same one there for 8. So it means basically all the terms from here, so if we add all the way up to, let's go back to 8, and we still have there, 10 choose 8. Right, this is still divisible by 3. Then all we have left is 10 choose 9, x9, plus 10 choose 10, x10. So what we basically wrote out now is that from here all the way till here is divisible by 3. Great, that simplifies our problem quite a lot, because the only terms we need to focus on is those two and these two. So if we want to go write this S congruent to mod 3, we will only have 1 x0 plus 10 x1. Mod 3 of all of this would be 0, and then we have 10 x9 and x10. Yes?
But 10 choose 0 and 10 choose 10 are also divisible by, no, sorry.
Okay, great. So that's what we're left with. And you can go right, simplify this. The 10s are just congruent to 1 mod 3, so we can go write this as x1 plus x9 plus x10. We'll just keep the mod 3 there. Right, so this is basically boiled down to how many ways. Just remember they're all either 0 or 1. So if all of them 0, great, that's a solution. Or if one of them is 0 and the other 3 are 1s, that's our other solution. So the number of ways we can basically assign them to be 0 or 1, we have one solution for when all of them is 0. We can make that, we have 4 of them, and we're going to choose 4 of them to be 0. Right, and that's just 1. And then our other solution is if only one of them is 0. So we have 4 of them, and we pick one of them to be 0. And this gives us 5. 5 solutions to which that will be congruent to 0 mod 3. Right? And if you go back, we still have our x2 to x8. But the point is that their values of x2, x3, x4 until x8 does not influence whether S is congruent to 0 mod 3. So it means they can basically be either 0 or 1, it won't influence it. So we have 5 solutions for these ones, and then for 2 to 8, that is basically 7 of them that could be either that, and we're going to multiply it by the 5. Okay. So where the 2 to the 7 comes from is x2 can be either 0, 1, x3 can be either 0, 1, and there's 7 of them, so 2 to the 7 times 5. And that gives our final answer of 640. Any further questions about that one? Okay, great. Then pigeonhole principle. Okay. Okay, so that's basically the statement of pigeonhole principle. You could also write a more general version, which I'm just going to add here, is basically if you have kn plus 1 objects that are put into n pigeonholes, then at least one pigeonhole contains k plus 1 objects. Great. Let's look at our first example. Okay, so this is the very basic idea of pigeonhole principle, which is actually quite useful in solving quite complex problems, you'd be surprised. So in this example, we have 4 colors of socks, and they're all in the drawer. And the question is, how many tries, how many times should you pull out a sock?
I think it's 5.
5 times. All right, so the answer is 5. Why? Because so with pigeonhole principle, every time you're basically going to pick your pigeonholes. And this is usually the hardest part of the problem, is deciding what to allocate to be the pigeonholes. So in this case, we're going to make it the different colors, which seems very natural now. So we're going to make red, blue, yellow, and black. We're just going to create 4 pigeonholes, or boxes. It's easy to think of it as boxes. So the first sock you pull out could, let's just name them, red, blue, yellow, and black. The first one you pull out could easily be red. Alright, so now we have 1 here. Second one you pull out could be red, but it could also be yellow. The last one could be blue. Again, you could have another one blue, like this blue. And the 4th one you pull out is black. So after you have pulled out 4 socks, it's still possible that you don't have a pair. But by the time you pull out the fifth sock, the only option is that it's going to go into a box that there is already a sock in. So it will have to be one of these boxes, meaning added here, for instance, you have 2 socks of one color. And this is, we're going to apply this concept repeatedly. And you'll see, choosing the boxes can be quite tricky, but it almost immediately proves quite complex questions if you just apply the idea of basically dividing it into boxes. Okay. Next one. See, a lot of the questions really look like number theory questions, but they are in part, but pigeonhole principle really helps to solve them. So, what is our boxes going to be? Our pigeonholes?
I think it's n.
N? Okay, sure, we want there to be n of them because we have a set of n plus 1. But what are they actually going to be? Like we said, each sock is basically, the color of sock is going to be a box.
The numbers
So you basically...
numbers up to n.
Right, but we want them to be, we want to have the elements in the set and we want to be able to divide them into the boxes. So if you have the numbers 1 to n, how do you prove where will n plus 1, in which box will n plus 1 go into? Because it can't go into a box that is just 2. Okay, let's see here. A and B. So A and B is just any element of the set. So the idea is that the boxes you create is basically every element in the set will be able to go into a box. So the boxes should basically cover the whole space of what all the elements could be. Yes?
Set of h plus 1.
The set of
H plus 1 is.
h plus 1.
Oh, it's n.
It's-
Oh.
It's an n, I'm sorry. So the problem with making the boxes 1 to n is you'll basically have this is 1, this is 2, meaning the only thing that can go into this box is the number 1, and only thing that can go into this box is the number 2. As in there we had a box, the only thing that can go into the box is a red sock, and we had more than one red sock. And you can do this, but you'll get to n, right? But what if you pull the element, which is n plus 1, out of the set? Any other ideas? Multiples of n. Almost. In an I somewhere. Also close. We're going to do it mod n. So we're going to create this box. It's for all the elements that is congruent to 0 mod n. This box is for all the elements that's congruent to 1 mod n. This box is for all the elements, I'm sorry, no, that is, sorry, for 2 mod n. And so we're going to go on, and because there is, our last box is going to be congruent to n minus 1 mod n, right? Because n mod n is just 0 mod n, so it's the same box. Okay, so, yes, so number 1 would go into this box, depending on what n is. Number n plus 1 will go into that box, because it's congruent to 1 mod n. So for every possible value that you could have in that set, it will have to go into one of these boxes. Okay, and we see that there are n boxes here, from 0 to n minus 1, so that's n boxes. So we basically have n boxes, and we have n plus 1 elements. Yes?
But then wouldn't it be exactly the same as before? Because you have the same amount of boxes.
You have the same amount of boxes, but what goes into the boxes, or what you call the box, as in what can go into it, is different. As in, if you say the boxes are just 1 to n, you just say that is the box. Then just the number 1 can go into box 1. But if you say the box is for all values congruent to 1 mod n, then is that? So it's basically the same idea, but you need to create the boxes in the sense that any possible element could go in here, because our elements aren't just necessarily smaller than n, as in they can fit into a box, to the list of boxes 1 to n. Okay, so the idea here is we have n boxes, and we have n plus 1 elements. Right? And by pigeonhole principle, we know that this implies at least one box will contain more than one element. Okay, so basically, in one of these boxes, there will be at least 2 elements. And our goal is to prove that there exist distinct A and B, so different values of A and B in S. So basically 2 elements in that set of S, such that their difference is a multiple of n. So let's say A, we choose A and B to be 2 elements that is in that box. Then, since A is congruent to 2 mod n and B is congruent to 2 mod n, it means A minus B will be congruent to 2 minus 2 mod n, which is 0 mod n, meaning it is a multiple of n, divisible by n. Okay. So it's not necessarily this box, so this is just the example. But it means that in one of these boxes, or at least one of these boxes, there will be that there's 2 elements in that box. Obviously, if it's in 0, that's quite trivial, but any other box, yes?
Are the numbers in the set like natural numbers, or are they like in order, or are they just random numbers?
They're just random numbers. So it's just a set of any integers. Okay. But it makes sense to you guys that when we take 0 mod any number from 0 till n minus 1 of that number, that all natural numbers can fit into that. Right, so if you have mod 3, any number will either be 0 mod 3, 1 mod 3, or 2 mod 3. Right? All numbers, all integers, will be able to be in one of those classes. So all numbers will be in one of these boxes, and that's why we can apply it in this manner. So in this case, we have 51 numbers. So ideally, we want 50 boxes or less than 50 boxes. All right. So I'm just going to do this one for you. What we're going to do is we're going to take the numbers 1 to 100, and we're basically going to put them together in pairs. The pairs are going to be 1 and 2, 3 and 4, 5 and 6. So we're going to so we have 99, 900. And we're going to make these pairs, yes?
I said we're going to choose 51 numbers.
Say again?
How come we have 99 if you have to be also choose 51?
Yes, so we only have to choose 51, but our boxes that we create need to be the numbers that we can choose, which is the numbers 1 to 100. All of them need to be able to go into our boxes. So our boxes need to be in such a manner that for all the numbers we choose, because if I stopped here at 50, 51, then for any numbers greater than 51 that I chose, I would not have a box to put them in. So I'm basically creating the first box is only for the numbers 1 and 2. The second box is only for the numbers 3 and 4. The third box is only for numbers 5 and 6. And so I'm going to go on. So I have a 9900. So only these two numbers can go in that box. So if I pick 1, it's going to go in this box. If I pick 5, it's going to go in this box. Okay? It means every number I pick can go into a box. This is different from what we had previously because you wanted the boxes 1 to n, but we can pick any number. And that number is not necessarily smaller than n. We just pick n numbers. In this case, we have a limited set we can pick from. Okay, so the idea is, again, here we have 50 boxes. These are going to be a total of 50 boxes. And we're going to pick 51 numbers. Okay, and this means by pigeonhole principle, there will be at least one box that contains 2 elements. Okay, right. So it means that we'll, as our elements come in, as we pick numbers, we'll maybe put a number in there. Let's see, it's going to be 1 we put in there, put a 5 in here, we put 100 in there, we go back, we put a 4 in there, and we put a 6 in here. It means we have this box that has 2 numbers. Now, this is the example of the box 5, 6. It could be any of the boxes. The point is that we will have a box which is basically k and k plus 1, because that is how we made our boxes to be. This is going to be the 2 elements that could be in that box. And this box will have both elements in them. But k and k plus 1 has no prime divisors. No common prime divisors. So we are done. Okay. Example 4. Okay, so for this one we're going to do two cases. Because if we're thinking of it from this, like we have it here, the natural thing you would want to do is you would want to make the boxes the number of friends that every person has. You would not want to do that? Someone there is shaking their head. Anyone has an idea that they would immediately want to do? Yes?
How would you differentiate
Okay. Right. But there are n people that could be friends with. There are n people to be a friend with. It's hard to say. So if for every one person that could have multiple friends, you want to put all the people. Okay. The problem with that is also they could be in multiple boxes. Meaning, let's say you have John, Peter, and Mary, right? But you want to make a box saying everyone that is friends with John. So, friends with John. This is basically what you want to make your box. So, Peter and Mary, let's say they're both friends with John. So they can both go in here, Peter and Mary. But the other box is friends with Mary. But let's say Peter and John are both friends with Mary. Then Peter can also go in this box, and John can go in this box. So Peter will not be in only one box, it will be able to be in multiple boxes.
Could you say for your conditionals, like people who have one friends to all the way to people who have n minus one friends?
Can people not have no friends? I know it's sad,
yeah.
but... Okay, exactly. So it is 1 to n, but someone can also have 0 friends. Someone also...
No, I just wanted to ask if 0 is actually a number.
Okay, so you can also have 0 friends. Okay, so the boxes I would naturally want to go for is people with 0 friends, people with 1 friend, people with 2 friends, 3 friends. Okay, until n minus 1 friends, because you can't be friends with yourself. Well, you could, but yeah. So you can't be in more than one of these boxes, you all agree, because you have a number of friends, so that puts you in the box. The problem now is if you look at this, this goes up to n minus 1, but there's also 0, so this is n boxes. Right? And we have n people. So, what do we do now?
If someone has 0 friends, then they can't. Then the person with n minus 1 friends can't be friends with them.
Okay, exactly. So we're going to break this into 2 cases, and one of them is what he said right there. So let's just say case 1. Okay. Okay. And this is someone has 0 friends. Alright. Okay. You could do additional case where it is more than 1 people has 0 friends, but then immediately we are done because 2 people have the same amount of friends. So we're going to only actually look at the case where one person has 0 friends. Alright? So then you have n minus 1 people left. And every person now cannot have every person cannot have friendships with the 0 person, right? For every person, there's a maximum number of n minus 2 boxes, okay? But we're also taking away the 0 box because we only said 1 person has 0 friends. Everyone else has at least 1 friend. So it's going to start from 1. So this is then basically n minus 2 boxes, but we're ignoring the person with 0 friends, which is not nice, but for now, we have n minus 1 people. Okay, And we apply pigeonhole principle to this, which means at least 2 will be in the same box, meaning they will have the same number of friends. The second case is, this is a very social group, and everyone has at least 1 friend. Okay. And what changes in this case? Nobody has 0 friends. So where we have a 0 box there, it's going to start from 1 here, 2. And so we're going to go on. We still have n minus 1. But now we have a total of n minus 1 boxes and n people. Pigeonhole principle applies, and you can. So basically, this is the only 2 cases that it could be, and therefore, if we proved it for both, it's true. Except for the last case, possibly where more than 1 people has 0 friends, and then we're done as well. Okay, that's our next question. So that's basically, if we had maybe, if it said 4 distinct numbers, you would have 1, 3, 7, and 9 has that property. Let's see, the sum of any 3 of them is a prime number. So now is the question, is it true for 5? Yes? Okay, so this is a quite nice solution. We're going to do this mod 3. Okay, so we're going to create 3 pigeonholes, and it might become clear later why we're doing this. Okay, so if you have mod 3, as we said earlier, it's either 0 mod 3, 1 mod 3, or 2 mod 3. And that's always your 3 options. All right? So we have 5 numbers, right? And we're dividing them into 3 boxes. So, well, there could be a number in one of each boxes, and then a second and a third in the other boxes, or maybe both of the 2 extra in one of the boxes. But the idea is we only need the sum of any 3 of them. So in case there is a number in every box, so from our 5 numbers, one of them is here, one of them is here, and one of them is here. And just saying this is any numbers, right? So if 3 of them is at least distributed like that, then we would have a number that is congruent to mod 0, and then let's just call it, what's the fun letter? A1 plus A2 plus A3. Let's say that is 3 above 5 numbers. Then they would be congruent, mod 3, to 0 plus 1 plus 2. And that would just be congruent to 3 mod 3, which is 0 mod 3. And then we're done. We're done because we just showed that their sum is then divisible by 3. But we also know that they're distinct, meaning that, their sum must be at least greater than 3. Okay, so let me just start here. Their sum is at least greater than 3. Say again?
I think one of the numbers is 0.
Positive integers.
Oh.
Okay. So because they're distinct, their sum is at least greater than 3. But their sum is also divisible by 3. And that directly implies it can't be a prime number because it's divisible by a prime number. Okay, so case 1 that we used here is at least 1 in each of the boxes. I would put 1 in each of the boxes, at least, but we showed if that is true, then we have sum not a prime. Okay. Our second case would be, okay, so we're assuming there's not at least 1 in each of the boxes. So just for example, we're going to divide the other 3 numbers between those 2 boxes. All right? But by the pigeonhole principle, we now have, so we're ignoring one of the boxes. We have 5 numbers and now only 2 boxes. And what does this mean by pigeonhole principle?
3.
Yes.
3
So
numbers.
one box has at least 3 numbers. And if we have 3 numbers in one box, it would mean they all 3 have the same value congruent to mod 3, meaning they are divisible by 3, and we still have this that our sum must be greater than 3. So basically the same argument, this would mean the sum is not a prime. I'm going to say divisible by 3. And the last case is basically trivial, where you say all 5 numbers go into one box, irrelevant of which box it is, where again you have more than 3 numbers with the same mod 3. And then we're done. So the challenging part in this question specifically was choosing the boxes, because this is deciding on mod 3 would need some spark of creativity. I think you are choosing 3 numbers though, so that might be some indication you need 3 numbers, but yeah, it's sometimes a hard thing making that jump to get to the number of what exactly you're going to call the boxes. Let's see. Ooh. Last one. Okay. Anyone have any suggestions? Yes.
You could start an extreme case where the points are the furthest away as possible from each other, with 3 of them being the 3 vertices of the triangle.
Okay, that is, you could definitely immediately say 3 of them could be on the vertices, and then they're all 3 distant 1 apart. What would you do with the other 2?
Well, you can sort of show that just from that, the maximum distance that they can be apart is because the height of that triangle is root 3 over 2.
Okay.
So if you take that, so you can sort of start moving. So if you take 5 points, they sort of going to have to be.
Try bringing pigeonhole principle into it. Let's see, she was first.
You draw the midpoints together and you'll get like 4 triangles on the inside.
What made you think of the midpoints?
Well, I just wanted to divide it into 4 equal triangles.
Okay, so we have 5 points. So it would be great if we could have 4 boxes, as in 4 areas where the points could lie in. And it also helps that this distance is a half, and our side length here is 1. So if you mark all the halves, and you connect them. So this is a half then, and this is a half. And similarly for one's inside as well. So now you have 4 equilateral triangles, yes?
Can I have a different suggestion?
Go for it.
So, so you draw a half radius around all the corners, which is like the furthest part,
You're right.
and then you'll find like right in the middle there's a point that one can go, like 1 point, and then if you put a point in there and you draw the radius, it already covers the whole triangle, so you're gonna have to put a point in anywhere that's already covered.
If you put the point there, yes, then the other points will be within, at most a half away from it. But is that a proof for if you don't put the point there, that it's maximum a half apart?
Well, if you don't put the point like there in the open space, it's gonna be in a space that's less than half from the corner.
From the corners. Oh, so you want to put them at the corners and then in the middle. And then I mean, if you justify it step for step, that could be a proof as well. This one is nicer though. So yes, for most of these questions, there are alternative proofs, especially for the ones there as well. But the idea is to also try and look for it with pigeonhole principle, because it's sometimes so fast and you can execute it so well. Okay, so back to this, we have 4 triangles, which is going to be our 4 boxes. So box 1 is it could be anywhere in this triangle, box 2, box 3, and then box 4. But we have 5 points, which means 5 points, and we have 4 triangles. And this implies by pigeonhole principle that 2 points, at least 2 points, will be in the same triangle. Okay, and within this triangle of side length 1, side length half, the maximum distance those 2 points could be is a half from each other. Okay, we did not get to doing the 2 challenge problems up there, but they are quite nice. The one there, the first one is quite similar to the other one we did, as in it sounds very similar. It's quite a different way, but it has a nice proof using pigeonhole principle. But if you could find any proof using pigeonhole principle, that's probably going to be very nice. And then the next one is also a bit harder, but please try to do it. I'll see if I could maybe make some solutions for the challenge problems we didn't get to. Okay, thank you guys.